evaluation metrics reveal the true quality of your model's performance or prediction. Welcome back to my channel. Hope you all are doing good. Today we are going to discuss about the other evaluation metrics which are responsible for your classification algorithms, and by end of today's video you should have the understanding, the fundamental understanding on how we are going to work on, or what are the metrics responsible for your classification algorithms, and those are the really important metrics which are needed or which are helpful to understand how your model performs. So let's start with our topic today. So what's the first metric we are going to discuss is on balanced accuracy. So what is a balanced accuracy, guys? It's a metric, again, very useful for imbalanced datasets. And how it is getting calculated? We are going to consider the average of recall for each class. So in case of a traditional accuracy methods, for any kind of balanced datasets, it is very reliable when the number of samples is in each class is equal, right? In case of traditional accuracy, or when we are calculating our accuracy on balanced datasets. And when in case of your imbalanced data, accuracy might not or is not performing well, and we have already discussed that point. So to handle that, we are using balanced accuracy. We are adding one more word, balanced, with accuracy. And how we are calculating? We are calculating on the formula such as sensitivity plus specificity divided by 2 in case of binary classification. And when we are considering, for multi-class, then in that case, we are just considering the summation or the average of your recall. So this is how your example or formula looks like. Is the summation of recall, you can see. And what is recall, guys? True positive divided by true positive plus false negative, and it is going to calculate for each class. Recall is going to be calculated for each class. Suppose if we have 5 class, that 5 times it is going to calculate the recall. Then it is going to add it up. Then after that it is going to divide it with 5. So for binary class, it's a simplified manner. And how we are calculating? We are just adding recall with specificity divided by 2, and this is the formula. For sensitivity, or in short, we are telling that as a recall, that's true positive divided by true positive plus false negative. Then for specificity, or which we are calling as a true negative rate, that's true negative divided by true negative plus false positive. Let's see one example how we are calculating or how you are achieving your balanced accuracy. So this is how your confusion matrix table looks like. So in this table, I have 3 true positives, 1 false positive, 4 false negative, and 12 true negatives. Okay. And if we want to calculate recall, how we are calculating? We are just going to use the formula true positive divided by true positive. Let me get my pen. True positive divided by true positive plus false negative. So my true positive is 3. So I'm taking 3 divided by 3 plus 4. So I'm getting 0.42. Recall, so I'm calculating for disease, because disease is 1 class, healthy is 1 class. So I'm first calculating for disease, then I'm going to calculate for healthy, and here I'm telling it's a negative class. Calculating for disease is my positive class, and for healthy I'm getting it's 0.92 when I'm adding up, like after applying my formula. And when we are seeing this, what we are observing, this is a binary classification, right? Because we have only 2 class, binary. It's a case of binary. So how we are going to calculate for binary? This is my balanced accuracy. We are just adding specificity with sensitivity. So this is my sensitivity, this is my specificity. So I have added it up and I have divided by 2. And in real scenario also, we are adding these 2 and we are dividing it by your what? Number of classes. So I got my balanced accuracy is 0.67. However, when I'm taking accuracy, this is how my formula looks like, right? True positive plus true negative divided by total predictions. And that total prediction is containing true positive, true negative, false positive and false negative. And I'm getting my score is 0.75. So when I'm telling 0.75 as compared to 67, that means somewhere I'm telling that my normal accuracy is coming high, right, as compared to your balanced accuracy. And when I'm with my 67%, I'm telling that uh, uh, my minority class or my poor or what I'm telling here, I'm telling that my accuracy or my output or my prediction for disease is happening poorly here, right? So this is how my balanced accuracy comes into picture. Now we will understand ROC-AUC curve. ROC-AUC curve again is a metric for binary classification, and it can be used for multi-class as well, but most of the times we are using it for binary. And what it does, it plots the true positive rate and false positive rate. So in your model, whatever true positive you are getting and false positive you are getting for each class, it's going to take that all those thresholds and it is going to put it in a graphical format. And what is ROC curve does? In case of like ROC and AUC both are two different concepts, guys. So ROC is a curve. However, AUC is a value which is determining that whole thing. So my ROC curve it visualizes the the model distinguishing between positive and negative classes, and we are defining few thresholds. It's going to take those, or it is going to calculate the values for those threshold, and it is going to graph it or plot it. However, in case of area under the curve or AUC, it provides a single score to measure the complete separations or the positive and the negative and everything. So higher AUC score means I'm telling that my model is better performing and it is differentiating the classes. However, AUC with 1 is getting represented as a perfect classifier, and AUC with 0.5 is getting represented as random case by model. So what is the formula? What is the full form of ROC? It's receiver operating characteristics. These things are very important, guys. Again, and I'm telling you need to remember this. If you are not able to memorize, just go through these videos repeatedly, multiple number of times, and understand it. So what is ROC? Receiver operating characteristics, and there are few features here to consider. So one is it helps to choose the best classification threshold. So suppose you are defining threshold of 0.4, 0.7, 0.6, 0.9 like that. Out of those thresholds, which threshold is good? It's going to tell that. And with that, what exactly is happening? We can see how balanced your positive with your negative, or the true positive with your false positive, how balanced the data points are. Then it's going to compare various models. Like it is very helpful or very useful when you are comparing multiple models. So if you take one model, you can plot, and if you take another model, you can plot that model's classes. And suppose model A and model B. Model A is all classes you are going to take thresholds and you are going to plot. Model B is all classes you are going to take and you are going to consider the thresholds and they are going to plot it. So that is one more helpful thing. And to evaluate the diagnostic tests, so in case of very a major sector or very sensitive cases where like for detecting cancers or for understanding cholesterol levels, so it helps to measure the concentration in the blood, right? Because blood is the main factor which is driving all the tests, or which is leading to tell you the most of the disease. So to evaluate that, This is very helpful, ROC curve. Then to understand the performance of the model regardless of your class imbalance and all, this is again very helpful, because accuracy is not going to give you that particular thing, because accuracy is bias most of the times for imbalanced classes. So here I have taken one example, just the way I have told you that we can take different thresholds. I had taken the probability, predicted probability for 5 patients. So here again we are considering probabilities, right? In case of ROC curve. So this is my actual value and this is my predicted probability for getting that actual value. So how, what are the thresholds I have taken? I have taken 0.5, 0.7 and 0.9. So first I am going to calculate for threshold 0.5. So my predicted positive is greater than 0.5, right? That means out of my, like this is my predicted labels, right? This is my predicted labels, 1, 1, 0, 0, 0. And my confusion matrix is going to be what? So this is my actual, right? This is my actual and this is my predicted. And my confusion matrix is going to be true positive, right? False positive, right? Then this is what? False negative, I believe, and sorry, true negative, false negative. My bad, I think this should be false negative, true negative, like that. So these are my predicted labels. That means it will plot it like this. It will plot it like this, how it's coming up. This is my actual. This is my predicted. That means I am telling that this should be 1, 1, 0, 0, 1, and here it should be 1, 1, 1, 0 and 0. That means my true positive is what, guys? This combination about the count of these two. So I am getting 2. Then my false positive is going to be 1, right? This. Then false negative is going to be this, and true negative is going to be again 1. So like that I am getting it, and I am calculating my true positive rate and false positive rate. How you are calculating? True positive rate is your true positive divided by true positive plus false positive, right? And false positive rate is false positive divided by false negative plus true negative. So this is how I am calculating my outputs. So once I am getting it, I am going to note it down. Then I am going to calculate for my next threshold. So for my next threshold 0.7, my predicted levels is going to be different. So instead of 1, 1, 1, 0, 0, it's going to be 1, 1, 0, 0, 0. So here I am getting true positive 2, then true negative. Sorry, my bad. True positive 2, false positive 0, false negative 1, and true negative 2. So I got this. Then after that I am again calculating this DPR and FPR, that means true positive rate, false positive rate. Then I'm noting it down, these values. Then I'm taking my next threshold. I am getting my predicted labels there. Then my confusion matrix is changing. So I'm getting 1, 0, 2, 2. And I'm getting my values DPR and FPR. And this is my ROC curve final table. So this is my FPR data points. This is my TPR data points. And this is how my curve looks like. Then we will understand my log loss. So log loss again is a metric of classification model which is helpful to measure the performance of a model based on the probabilities. What it does, it helps to quantify the penalty, or what is the penalty for incorrect classification and penalizing the confident. That means wrong predictions, in case of your real scenario, wrong predictions are going to be like very severely affected with less confident ones, right? So it is going to penalize the confident, or it is going to penalize the confidence percentage of your model. And when we're talking about lower log loss, that means it indicates a perfect or better performing model. And it is again, there is another term for log loss when we are talking. It's cross entropy loss. It's very important concept in case of deep learning, guys. This is an important metric in case of deep learning, however. Or we are calling that as a logistic loss, cross entropy loss or logistic loss. And this compares the true labels with the predicted probabilities. And like I already said that it is analyzing the predictions where the confidence is high, right? Where the confidence is high, because if model will tell confidently that a wrong output, it is going to tell you the correct, that means the model is predicting wrongly, right? One example for that, if your model is predicting 99% of probability is class A, it's going to be class A. However, when the true class is B, then the loss is really very high, right? That should not happen. However, if a model is predicting 51% of probability can be A, and then the loss is lower, right? That means we still have chance to improvise the model. We have still chance to improvise the model. So, in short, the correct predictions with low confidence, still has very low loss, right? When the model is confidently predicting the wrong output, right? So that's how a log loss looks like. And there are few cases, huge cases. It's used, or like I can say limitations, use cases, you can term that. So one, primarily it's getting used in classification problems, and it's a loss function, and it's a standard loss function for logistic regression. In case of logistic regression or a binary classifier, it's getting used. And I already said that it's very helpful in case of neural networks when we're talking about cross entropy, or this is the term, right? Cross entropy loss. So there is a very famous term called cross entropy in case of neural networks. And this is the formula for that. For an entire data set, this is the formula. How we are calculating? We are calculating the average of losses over all samples, and this is the formula. You don't have to remember it. However, for your reference, I am keeping all the formulas. The important one I am telling that you need to remember. So just go ahead to those formulas whenever I am telling that is needed. So here n is going to be a total number of samples, and here p, when we are talking about p, these are nothing but probabilities of all your samples which you are considering. Then we have Matthews correlation coefficient, MCC. MCC is a very good metric, and it is useful for evaluating both binary and multi-class classification performances. And here what it is going to give, it is going to give you a score between -1 and +1. And with that score, what we can understand, or what we can infer, that that score which you are getting, it accounts, or it consists of all 4 components of your confusion matrix. That's why it is very effective, because here all false positive, true negative, false positive, false negative comes into picture, and it is very reliable in case of imbalanced datasets. And it is considered, again, much more informative than F1 score and accuracy in case of binary classification, because this is the formula. This is how a formula looks like. It's true positive into true negative minus false positive into false negative divided by square root over true positive plus false positive into true positive plus false negative into true negative plus false positive into true negative plus true negative. So it's a combined effect, right? So I can say it's a more robust as compared to all kind of your metric. So these are your the full form of the shorts, whatever have been used in this. Then we have Cohen's kappa. So Cohen's kappa is a statistical measurement. What exactly you are doing? We suppose two similar groups are performing at the same time. It has to come to a agreement on which one is better out of the which output is better from which group, right? So in that case, Cohen's kappa comes into picture. Very useful in case of classification model and imbalanced datasets. Then human annotated datasets, like when human intervention is there in preparing the dataset, because most of the times we are getting the data from web, right, by scraping from SQL table, from different databases tables, and very helpful in case of multi-class classification problems as well. So when your accuracy fails, right, when your accuracy fails when your data is imbalanced and the agreement is very high just by chance. So Cohen's kappa is fixing that by adjusting those random agreements. So the score is going to be when it's ranging from -1 to +1. When I'm talking about +1, it's a perfect agreement. When you're getting the output as 0, that means agreement is equivalent to a chance. Negative means agreement is worse than chance. So this is how we have it's a part of your scalar and dot matrix, guys. So this is how your the property looks like, Cohen underscore kappa underscore score. And this is how your formula looks like, or the factor how we are calculating. So P0 minus PE divided by 1 minus PE. So P0 is your observed agreement, which is same as accuracy. PE is your expected agreement by chance. So when take one example here, I have shown that when two doctors are diagnosing a patient, they have to come to a agreement, right? Like they should be having a common understanding between them when they're operating a patient. So that is how, or that factor is getting controlled by Cohen's kappa. Then very important concept which we are going to understand, classification report. So classification report is a summary. It's a summary of all accuracies present for each class in a classification problem. So when you're talking about accuracies, what are the accuracies included in your classification report? We have precision, recall, F1 score, and the support. And we will see how we are calculating, or like what is the, because this is how your classification report looks like. This is the screenshot which is telling that. And it's a report getting generated by comparing different models, the predictions against the true output which you have, right, or the actual output which you have, or the actual class. So this is how your table looks like. So here your precision, recall, then F1 score and support, and we will see how we are getting it. So the first one is a class name, right? So the first one, so in this section, the first one is your class name. So when you're talking of class name, that means it is the number of classes which are getting used to predict the output. So in this report, we have two classes, right? The output class or the target classes which we are talking about. One is malignant and one is benign. Then we will go ahead to 2. So in 2, we have metrics for each class prediction. So in this section, we have the metrics. These are the metrics which you understood till now, right? Precision, recall, F1 score. So here I am telling that my precision is 0.97, my recall is 0.97, my F1 score is 0.97 for malignant. For benign, we have 0.98, 0.98 and 0.98. Then if we go ahead to 3, that means the actual instances for each class, or support. This is the support. So my support, how it is getting calculated? It is telling that number of data points that belong to each class. For example, to calculate these scores, this precision, recall and F1 score, to calculate this score, like just take this first one. To calculate this score for malignant, 63 data points have been used. That means these are the support points, right, in case of classification report. Similarly, for calculating the benign, to this course, this model has used 108 data points, right? 108 data points. Then what is the next step? We have fourth point, or the overall accuracy metric. So we understood, we knew what is the accuracy score, and this is the overall accuracy metric which we are seeing. That means it is telling that my model's accuracy percent is 0.98. Then we will understand the average, matrix average. So we have two matrix averages present here. One is macro average and weighted average. So this is the formula for macro average. So macro average is just straight to the point where it takes the average of each metric. This is the average of each metric or each class. That means for this, right? For we have two classes. One is what is that? Malignant, and another is benign. So the malignant class, it's going to take all the metrics like accuracy, precision, F1 score. My bad. We have used precision, recall, and F1 score, and it is going to add that, and it is going to get the average. Weighted average, again, it's a bit complex, and this is how it's calculating, and this is the formula. So it's going to consider the support along with the calculation for the output, and it is very good in case of imbalanced data. So this is how we are calculating. We need to consider the total support. That means it is going to add the total support, okay, and it's going to take the summation of support class into metric for each class, and it is going to add it up. Then after that, it is going to divide it with the total support. That's how we are calculating our weighted average, and this is how your classification report looks like. Whenever I am going to work on the next classification problem, I am going to show you that because we have used it till now, right? But we have used it in logistic classification or the logistic regression, example, real time example. But we will understand that by going through each from the next example. So we'll meet during our next video, guys. Thank you. Till that time, bye. That is all for now. We will cover the next classification algorithms in our upcoming videos. Whatever the algorithms are present, we will discuss that. Then if you really like the content, guys, go ahead and subscribe. Hit the bell icon while subscribing so that you will not miss the latest updates. Like, share your comments, share your valuable feedback, and till the next time, see you. Bye. Take care.